¿Qué ruidos?
Ahora. En teoría ya está.
Good morning. Good morning. Thank you for coming. We are in the having now the yearly review, I would say, for the doctoral school talk of Alex Jimenez Romero. The title is a climate-driven epidemiological model for peace disease of grapevines. Grapevines.
Okay. Well, most of you know me, but I'm here at the FIS doing my PhD. I've been here during 3 years already. And yeah, today I'm going to do my second annual control. And I will show you some work that we have been doing. Basically, I will going to present this climate-driven epidemiological model for peace disease that I will explain you a little bit what this is now. And some more results that are now in preparation. So, well, let's start with what is peace disease. This is a vector-borne plant disease that affects grapevines, and it's caused by a bacterium called Xylella fastidiosa. It has this name because it is very difficult to work with in the lab, and then it is very fastidious, and this is the real reason for, I'm not joking, this is the reason for the name. And well, as a vector-borne disease, it is transmitted by a vector. In this case, it is a spittlebug, which is a kind of insect, basically. And well, you can see here in this map that it is native to the Americas, and it's endemic in the US already, where it causes huge economic losses. For instance, in California alone, it has been estimated at $100 million per year. So it has a really huge economic impact. And now, very recently, in this century, it has been introduced in Europe. There are, for instance, in Spain, also it has been detected in Portugal, France. Well, so of course, there is a lot of concern because of the economic impact that it could cause on Europe if it gets established there and propagates through all the continent. No? So here in this image, you can see the symptoms of peace disease. Basically, what happens is that when the pathogen enters, let's say, the plant, infects the plant, it colonizes the xylem, and it starts growing there until it blocks the xylem. Then this causes water stress, and for this reason, you can see this brown part and also yellow part in the leaf. So in the end, this can cause, well, this usually causes the death of the plant. In this case, vines, but the same pathogen, different subspecies of the bacterium, also causes different diseases, also to almonds, citrus, and a lot of economic important crops. So some of the key factors to model this disease, we have it already here. First, the temperature, because the growth and survival processes of the bacterial population inside the plant are driven by temperature. And then, as it is a vector-borne disease, the vector distribution, because these insects are the ones responsible for transmitting the bacterium from one infected plant to other plants. No, sorry. So, as I have said, there is a lot of concern in Europe about the potential propagation of the disease. So there have been several attempts to predict the geographic distribution of these Xylella fastidiosa related diseases, not only peace disease, but the other ones also. And this has been done using correlative models such as species distribution models that I'm going to briefly explain what are these models. So basically, you try to predict the probability of presence of a given species based on climatic variables such as temperature, precipitation, or things like that. So basically you have presence data for the species you want to model or characterize. Then you have to generate pseudo absences. And with this data set, you train these, let's say, machine learning-like models to, given some climatic variables, predict the probability of presence, which is called usually suitability. So for Pierce disease, that is not a species, it's a disease. What has been done is species, so the people has been using species distribution models to characterize the geographic distribution of the bacterium or the geographic distribution of the vector. Both outcomes are independently proposed as a proxy for the risk of the disease, of having the disease. But what happens is that vector-borne disease are indeed emergent phenomena, so are not the, let's say, the simple sum of the components of the geographic distribution of the vector, the geographic distribution of the bacteria, but is something that arises from the interactions of all the components, and usually these interactions are nonlinear. So what I want to say is that you cannot just predict the distribution of the vector and the bacteria, and with those two outcomes try to predict the probability of the disease. So furthermore, there are other limitations for these kind of models. First of all, they lack crucial epidemiological information. Such as disease dynamics. There's no dynamics in this model, just a snapshot of suitability in the end. And as machine learning models or correlative models, they also have limited interpretability and explainability. So you can know which are the features that are more important to predict suitability, but you don't know really why or how is the interplay among these features or anything like that. But anyway, I think that these models are still useful. So until now, we had any piece of information, at least with these suitability models, you have something. And well, this you will know this sentence. So indeed, all models are wrong, but some are useful, and to some extent, these are still useful. And this sentence is also going to apply to the model that I'm going to show you now. So we asked ourselves these questions: if we could do something better to model this disease. We thought so, and we developed this mechanistic climate-driven epidemiological model that accounts for all these things here. So first of all, we take into account in a mechanistic way the temperature-dependent growth and survival processes of the bacterial population inside the plant. We also take into account the climate-driven vector spatial distribution, and we include epidemiological dynamics so that we can predict the outcome of the disease. And something that I like is that our model is mechanistic, so we understand all the parts of the model, so we can understand why there is risk in one place and not in the other pretty well, let's say, and instead of purely correlative like the previous models. So now I'm going to explain you a little bit how the model works. This was published in this journal, so if anyone wants to check it, you can check it there. So first, let's start with the general scheme of the model. It is indeed very simple. So we have an initial infected host population. The vectors are going to feed on those. I didn't say it, but the vectors usually feed on those plants. But as the plants are infected, they can get the disease also, and they become infected for the rest of their life. And when they feed on other susceptible plants, they can transmit the disease to those plants. Then there are new inoculated hosts or new exposed hosts, as you want to say, that now they have the bacterium inside. So this process, this first process, is modulated by the vectors, and we're going to model it through what we call the transmission layer. So it's one process, basically. Then the thing is that these new inoculated hosts can develop or not the disease in the end. So this is driven by the growth and survival processes of the bacterial population inside the plant that are driven by temperature. So we are to model this process of going from exposed to infectious, uninfected. We are going to model it through this, what we call the climatic layer. So some assumptions that we are making here is that, well, we are using these databases, so our model is based on these spatial cells, which are 81 square kilometers each cell. So we assume that there is only local disease propagation within the cells, but not disease propagation among the cells. In the end, as we are going to model the risk, this is not important because every some years we force the introduction of infected plants in each of the cells. So it doesn't matter if they come from neighboring cells or whatever. But this is how the model is constructed. And we are assuming also that inside each cell, there is a kind of a mean field approximation. So, okay, first let's see how works how we model the transmission layer. So usually in mathematical epidemiology, you use this kind of models that are called compartmental models, which are basically a system of differential equations. So we started with a general vector-borne disease model. And under some approximations and some reductions that are shown here, you can reach basically the SIR model that here you all know it. And in the SIR model, the dynamics are characterized basically by these basic reproductive numbers. So we have a single parameter model, let's say. And the good thing is that because we started with the general vector-borne disease model, we know how the basic reproductive number relates to the fundamental parameters of the disease. So something that we are going to use is that the basic reproductive number is proportional to the number of vectors in the system. So in our model that has several cells, if you know the vector spatial distribution, so let's say the quantity of vectors in each of the cells, you can use one value of the basic reproductive number in cell. Then we want to model the risk. So basically we want to know if the infected population is going to increase there or not. Then we're going to use this, what is called the initial phase approximation of the SIR model, that would be this exponential equation. So you can think about it as if we are considering an infinite number of host population. So we have just this exponential because we want to see if there is an increase or not. You will see it later. So now let's see how we model the climatic layer, which is the most interesting part. So in this disease, we have like two seasons. First, we have the growing seasons. That is when the pathogen grow inside the plant and then they develop symptoms. And then we will have another season, which is called the winter or curing season, that I will explain later. So during this season that the pathogen grows, we are going to model this growth. First of all, we have some data or measured data of the Xylella fastidiosa growth rate at different temperatures. We can fit this data and obtain a given function. And with this function, we can develop a metric, which we call modified growing degree days, that is related to the bacterial growth. So basically, this metric is just adding up in the whole period, the growing season, that is from April to October. We have hourly temperature data, so we just add up the contribution, so the growth rate at each hour. That depends on temperature. So this would be the modified growing degree days, and you can show that this variable is related to the bacterial load in this period. Then the thing is that in principle, the more bacterial load a plant has, the more probable should be that it developed symptoms or it get infected, something like that. So what we did was an experiment. Well, the biologist group did the experiment, of course. And this experiment, what we did was to inoculate the plants with the bacterium. And then we tracked the symptoms during a large period. And we recorded the temperature. Then we could compute this metric. And we could relate this modified growing degree days to the probability of chronic infection that is related to symptom development, basically. So, well, you observe here that the more your MGDD you accumulate, the more probable it is that you develop symptoms. And this is because you are indeed modeling the bacterial growth inside the plants. So then we jump to the winter season. So it has been observed, for instance, in the United States, that you can see some plants that get infected during the growing season that show symptoms, but then after the winter season, they recover, they get cured. So indeed, it has been observed that Pierce disease incidence depends on a little bit strange variable, which is the average minimum temperature of the coldest month. This is what was observed long ago. And what we think is that basically there is a death rate also that depends on temperature, on let's say cold temperatures, but this data is not available. So what we would like to do is to again feed this death rate as function of temperature and develop a modified cold degree days. We could not do so, but at least there is a cold degree days already that has been used in the literature for similar purposes. So we just took that definition. And still, you have to now correlate the accumulation of cold degree days with probability of curing probability. So again, there is no experiments, so we could not do it as well as in the previous part, but we could correlate cold degree days with this average minimum temperature of the coldest month. And because this is related to Pierce disease incidence, we could obtain this the relation between cold degree days and probability of curing, which is the inverse of probability of infection, of keeping infected in the end. So we can then, in the end, merge all these components together to build a model, which is indeed very easy. So it would be this equation. So the infected population at time t is given by the infected population at the previous time step, multiplied by this exponential, which was the transmission layer that I showed you before. Then this gives you the new number of exposed hosts. Then to see if these exposed hosts are going to become infectious for the next season, you first multiply for the growing season, that would be this. So you have the proportion of these new inoculated hosts that are going to show symptoms during the growing season. And then you multiply by the probability of keeping infected, not curing. And these are the number of infected and infectious hosts next year. So, well, what we want to study here is not the incidence, and indeed this equation is not a good one, let's say, to model incidence, but it's just an exponential. But we want to model the risk. So in the simulated period, what we are going to define as risk index is the effective growth rate of this equation. That remember that all this is computed using data, so historical data. So then it is easy to see that if this growth rate is negative, then there is a decrease of the infected population, then there is no risk there. And if it is positive, there's an increase of the infected population, then there is risk. And furthermore, because we are bounding this here for using the maximum growth, so under optimal climatic conditions, this would be 1 and 1. Then you have an exponential growth with this rate. So you can also differentiate different, let's say, risk zones or zones in which the impact would be higher, well, worse or whatever. So once the model was built, first we had to validate the model. So we have only one free parameter, which is the basic reproductive number. In the United States, there are a lot of data because the disease is endemic there. So we had data of presence and absence of Pierce disease for several years and locations. So we could use our model with different values of R0 and see which is the one that yields better results. I must say that in the United States, there are like 8 vectors that can transmit the disease. But in Europe, there is also only one. So the situation is a little bit different. So how did we fit the model for Europe? Here, we don't have this kind of data, but because it has been recently introduced. But we had to do another thing. So basically what we could, which is the following. We had data for the Almond-Leaf-Spot disease epidemic curve in Mallorca, which is caused by the same pathogen and is transmitted by the same vector that Pierce disease in Europe, which is Philenosus fumarius, an insect. So by fitting this data, you obtain the basic with an SIR model. You obtain the basic reproductive number for almond leaf spot disease in Mallorca. Then what we did here was just to assume that the infection rate is not going to change much because it's the same bacterium and transmitted by the same host. But what is going to change, and we know how it changes, is the mortality rate, because the host is completely different. Instead of vines are almonds. And just by changing this number that is known, we obtain this value for the basic reproductive number in Mallorca. And it seems right because it's lower than the one in the United States because there are less vectors. And the proportion to which is lower also makes sense, just from a biological perspective, but I cannot say more. But it looked good, basically. So then we finally applied our model to different places in the world. And what we observed was that all places that are currently affected with Pierce disease were identified as risk zones. But we also observed, I don't know, for instance, this part here, that is identified as high risk zone, but there is no Pierce disease there. This is not wrong because it can be that the conditions are favorable. But if you do not have an introduction of the disease there, it cannot propagate, no? But yeah, so what is happening here is that we are using this homogeneous vector distribution, assuming that the vector is everywhere in the same quantity. But for Europe, we have the vector spatial distribution that comes from these species distribution models. So we have that there are some places in which there is more vector and in another less vector. So using this vector spatial distribution, then you can simulate the model with a basic reproductive number that is different in any cell, and you observe that the risk is downscaled, that it makes sense. And still, all current affected zones with Pierce disease are classified as high risk zones. So our model is really precise. And then we also observed here there's risk also here, and it has been after the publication of the article. They also found Pierce disease here. So it seems that it's working quite well. Well, we did a web page in which there are a lot of results there that if anyone is interested, you can check it later, and I will show you something. And to conclude with this part, well, the most important thing is that the approach is quite general, so in principle could be applied to, so the framework, let's say, is general and could be applied to other plant diseases. And we found that the risk is increasing in this part of, well, in more places, in southwestern France. So as further work, we thought about combining our model with climate change scenarios to see how the risk is likely to evolve in the future. And this is precisely what we are doing now. We have already some results. I'm going to show it to you. Well, what's new? Basically, what I said, we integrate our our model with climate change scenarios. We use different warming levels, and we compute our variables using these climate change scenarios. Furthermore, we included an analysis of impact on wine protected designation of origin regions that I think is quite interesting. In the previous article, we analyzed the risk at the country level and also at the vineyard level. Here we included this level that would be in the middle. And well, some results. First of all, we check the suitability of both the pathogen and the vector. Here, the suitability of the pathogen, it's basically the growing and survival processes that we model mechanistically. And this is, again, generated using a species distribution model. So these are the current values for the suitability of the pathogen and the vector, and then we have the change at different climate change scenarios. So we observe that in general, the suitability for the bacterium increases. So in the future, under these global warming levels, the pathogen can live better, let's say. But for the vector, we have a decrease of the suitability of the vector. So in principle, you would find less vector. So then the question is that how will the risk evolve? So in the previous models, you usually had this, but you don't know how to merge it. The good thing is that with our model, we can say what is going to happen. So we applied our model and we try to answer this question. So what we observe is basically that the risk increases in the Mediterranean regions, but also from this +3 scenario, there's like a tipping point of propagation of the disease to more continental Europe. So for instance, in this part of France or in the upper part of Italy. So we also computed what is called the per-disease risk velocity, which basically means how fast a given value of risk is propagating through space. And we also observe that in those scenarios, there are not there are not a lot of points with high risk velocity, but from this scenario also there are higher velocities. And well, some nice results are also these country level, PD or region level, and vineyard level analysis. Because, for instance, I will show you just an example. If you check, for instance, France, it has very low risk at the beginning, and until in percentage, in the +4 scenario, for instance, is a huge increase. 7% of the total surface at risk is not that much. But when you check it at the PD or region, you observe that although 7%, only 7% of the surface is at risk, 40% of the PD or regions will be at risk. And if you check the proportion of vineyard surface, it's 80%. So what is happening is that basically the risk is concentrating in the places where there are vineyards. On the other hand, for Spain is the other thing. So Spain starts with a 7 and then decreases, which is also interesting. But the risk in PD or regions, it keeps similar. Indeed, it decreases also. So basically, yeah, I mean, it's interesting to analyze this in the appropriate scale to see the true risk of each country, for instance, not just at the country level. And okay, just to finish, something interesting is that we identify this +3 scenario, let's say, as a tipping point for propagation of the disease beyond the Mediterranean regions. And we also see that the overall risk is downscaled compared to species distribution models that can also be used with climate change scenarios. But we can answer why. So basically, we see that bacterial survival is difficult in Northern Europe, well, because of high CTD values, but now I have checked it in more detail. And also because of, so this is because difficult survival rates in the winter curing season, but also they don't grow that much during the growing season. So you don't have many growth, and then the little growth that there is there, it's killed during the growing season. So basically we observe that there is no risk and that it is very difficult to have risk. And we can answer why. So that's nice. And yeah, let's see if I can put this. So, okay. So we did this dashboard to show, it's a little bit slow because the data is quite heavy, but okay, yeah. We have some plots of the different, at the country level, for instance, the risk at different countries, or for instance, PDOs, this is more interesting, and also vineyards. So you can check, I don't know, each one of the vineyards that are provided by a given database, which is current land cover. And you can see the risk of each of the vineyards. And also, if anyone likes wine, you can check the different, for instance, PDO regions, for instance, Rioja, and you can see if it is at risk or not. In Spain, most of them are not at risk, but in France, for instance, you can see very interesting things. Well, this would be all. So thank you for your attention. And if you have any question.
Any questions there? I mean, you can explain in detail and. Hello.
Hi.
Yes, I have a question about the climate change. We consider up to 4 degrees increase. In that case, I imagine that there are a lot of things that will change in the natural ecosystem, and that may perhaps include another influence of another, I don't know, species or that may introduce a change in the model.
For instance, something that could happen is, so the results that I was showing, these ones is using the, so for each scenario in our model, you combine, let's say, the part of the pathogen and the part of the vector. No, we are observing that the vector decreases. So for instance, in Spain, so maybe you are seeing that in Spain there is no an increase of risk because the pathogen can live better, but you have less vector. But what would happen if a new vector is introduced? So what we can do is instead of studying this with the distribution of the vector, you can assume that the vector is everywhere, as we did in the previous. And then you see what would happen if a new vector gets introduced. But then the results, you have a lot more risk, of course, but yeah. And also, for instance, here we analyze this at the binder region, that it's not in the figure, but you have all the binders, but also could happen that in the future, the binders moved. So that maybe people, the vines cannot really be cultivated there, no? And people start moving the vines. This could also happen because of climate conditions and
Yeah, because one thing is the disease, another thing is the wine gets too much sugar or too much alcohol. And, I have a question regarding the model itself. The way you assume the model, understand there is no contagion. So basically, you just assume that each of these cells is independent from the other.
Yeah.
So there is no probability that these infect the near one.
No, but we force it. So in the end. Yeah. So in each cell you put an initial infected individual, no, and you run the model. You run the model for 7 years because the typical time is, let's say, the typical time scale of the disease. So to see if there is an increase or not. Then after those 7 years, you just move 1 year and reintroduce again the disease in all the pixels. So you every time are trying to see what would happen if I force the introduction.
You model the clone if you were introducing a few
infected,
bacteria and a few, few bacteria and a few vectors.
Vectors are always there. Because vectors, indeed, I didn't say it, but before the disease came, the vectors were already here.
Okay.
Yeah, it's a species of like saltamontes, of insect. It's always there, yeah.
Do you use data for the amount of vectors?
It comes from a correlative model. These species distribution models that,
Okay, so the problem they might be data for that.
There is presence data, but not for every pixel. So the way they translate this presence data into a map, let's say, would be this species distribution model.
Okay.
Yeah.
And then itself, so it got 80 kilometers by 80 kilometers.
Yeah.
So say it doesn't consider, I guess, any topographic inside
no.
rivers that may favor more vectors or less vectors.
No.
Humidity of that.
No,
these vectors to go where.
No, in itself, you just have the climatic variables that give you but for instance, if you go for a higher resolution data set, let's say, we did this for another data set that instead of 9 by 9 kilometers is 1 by 1. So you have much more resolution. And something that you see is that some parts here well, you cannot see it very well, but some parts here that when you use the vector, I think are at what we call transition risk, that the growth rate is very near zero. So you don't know if it decreases or not. When you solve it with higher resolution, you observe that there is a part, a linear part, let's say, like a river with a lot of risk, like and also the climate, yeah, it's different. But you have a gradient of risk in a pixel, no, the risk there, but zero risk in the other, and the mean is you don't really know. This is really interesting, and we are going to also do something about it. But yeah, so the resolution is also very important. This was 9 by 9 because it was a global data set, but it's really important.
Do you really want to compute for all the points in that data grid? I mean, who cares about points in which there is no gates nowadays?
Yeah.
One could say, well, let's focus on all of the specific region where there is
exactly.
And since we are assuming for now that there is nothing coming from all
we
can just take
exactly.
Specific and put a very fine grid over there and nothing else.
Yeah, but you need the data. So
yeah, of course.
But yeah. Yeah. There are things. Yeah, but yeah, it's not. But yeah. So the important thing in the end is in the vineyards, in the regions where there are vines. But also, this is only for Pierce disease. But somehow it's also a proxy for other Xylella fastidiosa diseases. Not exactly, because the winter curing part for vines is like very important, but for others like almonds, it's not that important. But the thing is that somehow this is also a proxy for other Xylella fastidiosa diseases. So maybe there are no vines, but there are olive trees. I mean, and you don't really need a lot of computing power to do it. It's not that. So, but for Pierce disease, the important thing obviously is in the vineyards or PDO regions, something like that, but not, or for instance here, you can say, see. But here, I don't know why we use all this extent. Now we are focusing just on Europe, also because it has been introduced. Yeah. Yeah, exactly. Here, I think that no. In Taiwan. Sí, pero yeah.
One question, you can go back to the maps that you saw at the end.
Oh.
So here you saw that in the worst case scenario, Spain, even in the global the risk is even lower. How, for example, Portugal also with worse, and also if you go to the town,
the rest.
Southwest is one of the regions that are very low risk. So how can you play that?
Yeah.
Do we have something to do with all the winters?
No, I think it's because of the vector. So if you see here, these, for instance, white parts are not at risk, or these parts, so the southern part of the peninsula is there is not a lot of vector because it's too dry, and then it's going to become drier in the future. So then there is not a lot of vector, and it's going to decrease by 0.2. So there is not enough vector. But this depends on the basic reproductive number. I mean, the vector changes the R0. R0 is 5 if you multiply it. So if you multiply it by 0.2, it gets 1, and then it's not going. So R0 is less than 1, then there is no. So these kind of results are, I mean, this comes from a correlative model. maybe the decrease is not going to be, it's not perfect, this model, I don't know. And also the R0 that we are using 5, maybe it's also not perfect. So, but in the model, we obtain these results because of the vector, basically. There is no vector in all this part. And if you see, so yeah, so here you have this transition risk. So indeed, you see that somehow increases the risk, but it keeps in transition. So there are some parts that are moving from no risk to transition, which is like they want to. So the transition is that usually is because by the part of the pathogen, it wants to spread, but there is no enough vector, and it's like, so this is very sensible to the parameter values indeed. See, exactly. So for the pathogen can live well, but if there is no a vector that transmits it, yeah. So in the case of Spain, is because of the vector, because you can see it here. The suitability for the pathogen is really high.
Just say something, I'm not completely agree with you. I think in southern Spain, it's what you say, but in northern Spain, it's high plateau.
No, yeah.
They are in Rioja or Rivera del Duero, you know.
Sí. Then it's climate.
Minimum temperature in winter is
Sí, exactly. Indeed, you see it here that in northern Spain, the suitability for the bacterium is 0 now, but you have a lot of vector, so they don't match basically. But in the future, for instance, something that could, yeah, indeed you can see it. So here you see that in the future, here it is going to, there is an increase of suitability. So from 0, you are going to have maybe 0.4 or something like that, whatever. And the vector here is almost 1, 0.9 or 8 or whatever. And there is no decrease there. So then here you see that you have no risk, completely blue, but here you start having risk, but in transition. So yeah, está ahí. Sí, no, yeah. So, but Spain keeps quite safe because a +4 scenario is, in principle, it's exactly. If you compare with Italy, France, yeah, no, sí. And also with the higher resolution data, for instance, this part of Galicia is going to, I think, have more risk because in the river there is risk now, and you don't see it with this resolution. So there, all depends on a lot of things, like and the resolution is important.
Okay, one is makes a little naive for some of the image so to the total population, they are wrong.
Yeah. So indeed here, I don't know where it is, but yes. See, I mean, in the end you have, well, this, yeah, it would be this, let's say. It will be the climatic suitability for the vector. So we assume that this is a proxy for abundance of vectors. The total population of plants. No, it doesn't matter. Like no. In this model, no.
The other kind of species that we are talking about, but maybe for example, we can have some other species like almond that have also a symbol of the
yeah.
They are not considering that.
No, but this would be in the part. So in the end, you would have a higher R0. So the good thing is that you have this part, no? So having a reservoir would, but yeah, we are introducing. So in our model, we are trying to propagate it all the time, the disease. So if there was a, so you are saying, okay, if there is a reservoir, there's never like a death of, you can always have this introduction, but we are already forcing it. But
these mechanisms of some plants that can after 1 year remove the bacteria and maybe that's in one another. Why you have that?
No, sure. Exactly. Yeah, but what the only thing that changes is that the number of vectors infected that you have there. Yeah, so yeah, and this is in the end given by this R0. See, so it's not that important, I think, but.
And the other question is when you present the first model, you have this video of France. How do you get that evolution in time? You are not considering
No, because I had data from 1988, 1981 to. Sí, exactly, claro. No, but in the future, I mean, I could also do this kind of video, let's say in the future, because what I have in the +3 scenario, for instance, are like a time series of 20 years of the typical climate that would be at a +4, +2 scenario, for instance. Then I can, and using that, it's how I compute these risk velocities. So I also have like 20, because there are climatologies that are like 20 years of 20 years.
More questions? Well, something that you didn't really do a broad introduction on the area. This disease, I mean, has become very relevant in Italy, from 2013, has affected all like trees in a very strong way, and they have taken out more than 20 million olive trees. So it has a huge economic impact. Now this is here and now the disease and the device has affected my daughter, but really, I mean, it was many trees in the school. It was the area of olive trees.
Yeah. Sí. And Apulia would be this part here. This is more or less the risk of disease right now, because we are already at +1.2, so it's very similar to this picture. This is the Apulia, and there is a high risk of pest disease. And for almonds, because the winter curing is not that important, they have even more. So yeah. So that it's interesting also that here there is this very huge outbreak of it's called olive quick decline syndrome. So, and we identify this as a high risk zone. There is no pest disease there because whatever, but they have the other one. Yeah.
Okay, thank you.
Thank you. Vale, sí.
Lo apagamos primero.
Claro,
Todo tipo de ruidos.
sí.